Hi folks, we're looking at number 18 from page 107, so they want us to find the b value that'll make this limit exist. Okay, and I'm actually going to solve this problem in 4 different ways. Now you might be asking, why in the world would I take the time to show you 4 different solutions? Well, because what I want you to see is how there's different approaches to a problem like this, and all of them sort of use some sort of knowledge either of calculus or what you're doing in advanced functions, and in fact even what you have been doing since grade 10. So if you're stuck with a question like this, say, as a thinking question, you really want to just sometimes try a couple of things that look like they might be related, and you might end up coming up with a solution, okay, or a good perspective to attack the problem. Okay, so in some ways I'm kind of going most complicated to least complicated. Okay, so the first thing I might look at here is I say to myself, well, I look at this denominator and I see that it's approaching 0. Okay, so if I have something where the numerator is approaching 0, well, the way in which to deal with a circumstance like that is to find a factorization of the numerator that will allow me to cancel the x minus 1 in the denominator. Okay, so in other words, I would need x squared plus bx minus 3 to have x minus 1 as a factor. In other words, it can be written as x minus 1 times some other factor here. Okay, and this is where the fact that this is a nice easy quadratic with an x squared, no coefficient, or a coefficient that's equal to 1, and here a nice simple prime number, and I realize that in order for this to be factorable, there's no choice for, first of all, this first position to be equal to x, and in order for the product of the last terms to be equal to -3, this has to be equal to plus 3. Okay, and so when I multiply this out, I get x squared, 3 minus 1, so plus 2x, and then minus 3. So here I see that if b is equal to 2, this expression is factorable with a factor of x minus 1, and I'll be able to cancel out that denominator and eliminate the problem. Okay. Second way I'm going to look at this is very similar, except it's a little more general, because this here really only works well if I've got a nice easy quadratic. Imagine if this were a cubic or a quartic, and I had to try to figure out how to make it have a factor of x minus 1. I certainly couldn't do it by inspection here. Okay, but I do know that if I have a polynomial and I divide it by another polynomial, okay, it's going to be this will be a perfect factor of the numerator if the remainder is 0 when I divide them. Okay, so if I divide these two polynomials, okay, x minus 1 must be a factor of the numerator if I divide them and the remainder is 0. So here, because I'm dividing by a linear, I can just use synthetic division. Okay, so I put 1b -3, and I'm dividing this polynomial by x minus 1, so that means we've got a 1 here. And once I do this division, so bring this down, 1 times 1 is 1, so b plus 1, and then here 1 times b plus 1, so b plus 1 here. Add them up, so I get b plus 1 plus -3, or b plus 1 minus 3. We end up with b minus 2. Okay, but in order for x minus 1 to be a perfect factor, this expression here, which represents the remainder, must be equal to 0. And so we get the same result. B would have to be equal to 2. Okay. Now, let's look at another perspective. So, again, similar to this, this idea that I need to show that x minus 1 is a perfect factor of this quadratic, I actually don't need to know to do the long division. Given that I'm dividing by a linear term, I can use the factor theorem to show that x minus 1 is a factor of that numerator. Okay? And the way the factor theorem works is I just take the value here, so I've got x minus a, in this case here a is equal to 1, and if I input that number into this polynomial, it should be equal to 0. Okay, so that's just a straight application of the factor theorem that you learned in advanced functions. So if I take x squared plus bx minus 3 and I evaluate that at x equals 1, I need this to be equal to 0. So 1 squared plus b times 1 minus 3 is equal to 0. And when I solve this, here 1 minus 3 is negative 2. Bring it to the other side. B has to be equal to 2. So another way of showing that x minus 1 is a factor of that numerator. Okay, that will occur if b is equal to 2. Now let's use a fourth solution to this same problem, and this is probably the most calculus of these solutions. Okay, is because the denominator is approaching 0 as x approaches 1. The only way for this limit to exist is if the numerator is also approaching 0. In other words, I need the limit of x squared plus bx minus 3 as x approaches 0. I also need this to be equal to 0. Okay? Because the only way for this limit to exist is if I have an indeterminate form. So let's come back here, and I realize, well, this limit on the left-hand side I can actually determine explicitly because this is just a polynomial function. And I know that a polynomial function has a limit at all points, and since it's continuous, the limit is equal to the function value. So this limit here I can just take, so this is just going to give me, I just realized I put 0, sorry, this should be the limit as x approaches 1. So let me evaluate this limit, just 1 squared plus b times 1 minus 3 equals 0, and similar to what we had before, b ends up having to be 2. Okay? So again, the reason why I showed all these solutions is because, sometimes depending on the perspective you take, you can find different avenues to get to the answer. Okay? Some, perhaps a little more complicated, others a little quicker. Okay? But each one of them worked, and each one of them was well justified. Okay? That's it. So remember, always keep an open mind when you're solving these problems.